Hi, welcome back. Today I'm going to cover a machine learning tutorial with Python. Last time we talked about machine learning and deep learning, and now we're going to use Python to code these concepts and see how the machine learning workflow goes. And today I'm going to use a toy problem. It's going to be a very short tutorial. And you can apply these concepts to any machine learning problem. If you're new to Python, this will be a perfect video for you. So let's get started. Last time I talked about taking a data set, splitting it into 3 parts, a training set, a validation set, and a test set. Once you do that, then you visualize your training set and you see the trends in your training set to understand your data. And this will help you create your feature vector. Your feature vector will have terms that try to mimic the data set. For example, if it's oscillating, you put sine in this feature vector. If it's exponential, you put exponential functions. If you want it to be a polynomial, you'll include x squared, x cubed, etc. Now, once you design your feature vector, you go to your hyperparameter tuning. You change your hyperparameters according to some metric, or you just try different hyperparameters, and then you run your gradient descent algorithm. Once you do that, you'll get your validation loss, your validation error. If you're not satisfied with the error, you go back and redesign your feature vector, and then you repeat that forever until you're satisfied. Once you think your model is good, you take the predictor and you test it on your test set. If the error is good, this will give you your generalization error, how good your model is to generalize over unseen data. Now we're going to try to do all of this process with a simple problem. And you'll see that in general in machine learning, it's always a very similar process. Some things change. Maybe it's not exactly like this, but this is the benchmark, the reference that everybody uses to build the machine learning problem or model. OK, so to code things in Python, I'm going to assume that you're not very familiar with Python or with machine learning in Python. So as much as possible, I will explain every line. And therefore, I'll write the code live so that you can follow me. And you can, if you want, you can ask questions. You can correct me if I'm wrong. You can see that I will make a lot of errors as I'm writing things. So let's get started. So to do that, I'll go and open a browser. Let me make it dark here. And I'm going to use Colab, because if you don't have Python, the easiest way to get started is to use Jupyter notebooks or Python notebooks, which are very easy to use for first-timers. And they're also very useful for testing machine learning problems or data science problems in general. So to do that, we'll go to Colab, colab.research.google.com. And if you have a Google account, you'll probably go into this page, and then you will select a new notebook. And now, in this framework, you can do 1 + 1. I know this is too simple, but if people are not familiar with Colab or with Python or with notebooks in general, they might find this a bit strange. So you'll see that it gives you an output for each cell here. So now we're going to import NumPy. And we're going to import sklearn. So sklearn is a machine learning library, which has a lot of algorithms that help you do your optimization and get your predictors. And in particular, we're going to use linear models. So we're going to import linear model. In fact, we're going to import something from the linear model. And this is going to be from sklearn. And import linear regression. We're going to also use Lasso, which is linear regression, but with regularization. We're going to also go and import model selection, which will help us do the splitting. Or of course, you can take the data and split it yourself. But if there are functions out there that can do the job for you, why not? And this will make your job easier and faster. It's very useful when you're building machine learning models or any framework to see if there are packages that are already out there that can help you do the problem yourself, so that you don't spend a lot of time building everything from scratch. And that's why last time I mentioned that, in the case of stochastic gradient descent, it's important to understand what's happening. But in general, depending on your problem, if your problem is not too complicated, there's nothing special about its optimization, then you might want to use optimization algorithm that exists out there so that you don't spend much time on it. All right, enough talk. So let's import a train test split. We might import more things later, but first let's go through the first step, which is create. Actually, maybe I should bring it back so I can come back to it anytime. It's fine. It's just above my head. So the training set, validation set, and test set. We're going to have to. Well, before we do that, we need to get our data set. How do we get this data set? In physics, informed problems or data science, data-driven science, there's this very common way of getting the data, which is simulating the data, generating the data yourself. So I'm going to just say get or generate data. And we're going to use this simple example of the data is a parabola. And it's a noisy parabola. So to do that, we're going to create x, the x-axis data, or xy. It's input and output. Our input is going to be between 0 and 10, 100 data points between 0 and 10. Our output will be this x squared. So we know what the actual model is, x equals y squared, but it comes with some noise. And that noise is given by this noise strength. NumPy has this function called random, which generates a random number between 0 and 1. So we want this random number to be between minus 0.5 and 0.5, and then we scale it according to this noise strength. So first, it's going to be the length of x, and then we're going to subtract 0.5. OK? And once we do that, is there anything missing? So one nice thing about notebooks is if I have a bug for some reason, because it happens all the time, you can just really test it in real time. And this is what you get. For example, I couldn't test it here because I haven't defined noise strength yet. So what's our noise strength? So here, before I start to get, I'm going to define my inputs. And my inputs are going to be given, well, we'll add them as we go. So here, our noise strength, let's say it's 3. And, well, this should work now. OK. We generated the data. It's noisy data between that, for x0 to 100, and also 100 data points that are parabola. And now we want to, what's the next step here? Well, we have to split it into training, validation, and test set. And we're going to use this train test split method, which returns, OK, split data. So it's going to be xtrain, xtest, ytrain, and ytest is equal to train test split. So this is going to split my training and test sets. And the inputs are x, y. And there are options. You can also look for documentation. You can shuffle the data, or you can keep it as is. And this is an important kind of input. I'll tell you what's the difference between shuffling and not. And so here, this is another one of our inputs and or hyperparameters. So we're going to shuffle the data. And another thing we can look into is how much of this test set are we putting on the side? What's the percentage of the whole data set? So this is test size is equal to, let's say, 0.2. I'm going also to define this new variable called test size. So we go back here and define a shuffle to be, let's start with false. And I'll show you what's the difference with false or true. In general, you want it to be true, but I'll show you here we have a difference between extrapolating and interpolating. And here I'm going to use 20% for the test set. Now, I want not only training and test set, I said also I'm going to test my model on the validation set as I'm building it. So we're going to take the training set. So here I'm going, instead of having the inputs being x and y, I'm going to take it and go to train. I'm going to take the training set itself and split it in two. And so I'm going to override the training set by xtrain xtest. Well, now it's not xtest anymore. It's dev. Sometimes it's called a dev set, but let's call it a validation set. And val. OK. So again, we see if we don't have errors, and then we proceed. We split the data now, and the next step is to visualize the data and see the trends in the data. Visualize. To do that, well, we're going to use a matplotlib. In Python, matplotlib is the most common visualization library. So let's start with creating a figure, plt.fig. Well, I can't use this unless I import it. So let's import it. From matplot.pyplot, import. Well, sorry, this is not it. It's actually matplotlib.pyplot that I need. So import this as plt. OK. So now this gives me this plt object, which is a plotting object. With it, I will create a figure, .figure. Now, there are different ways of using matplotlib. I'm just going to use the most simple one. Let's do simply a plot of xtrain, ytrain. And we're going to make it. We're going to make them dots, and let's make them black. It's OK. It's for black, and the line width here, the marker size is going to be 5. I don't know if that's good. Maybe 10. We'll do the same for test, and well, technically we're not supposed to look at the test set because we're supposed to look at it at the end. In reality, you're not going to look at the test set if you have enough data. But here, just to illustrate the point of difference between shuffling and not shuffling, I'll also plot the test set. So this is going to be validation set. Val. And this is going, let's make it blue. And finally, the test set was going to be green. Test. All right. So plt dot. We're going to x label, put an x label, x, and a y label to be y. And finally, to show the plot. We can also put a title and legend. Actually, legend will be useful. So let's put a legend. plt.legend. Train validation and test. OK. So we run this. OK, should not forget to run this first. So run these two, and now we see the data. I don't like colors, but OK, it'll be fine. Actually, we can do yellow. No, let's just keep it like this. So let's increase the noise strength a bit so that I illustrate the point of having a lot of noise. So let's make it more like 7, lucky number. Let's go with 10, decimal number. All right. OK, so now we have this parabola, but of course, you want to fit a parabola to it. You can't just fit any polynomial because you might overfit, underfit, and so we'll cover these concepts now. You can see that the first part is a training set. The second part is a validation set, and then the last part is test set, and you can see the ratios. Now, should you shuffle or not? That's the question. If I shuffle, then you can imagine that I'll be sampling randomly from the domain for the test, training, and validation sets. So you can see this is shuffled, and so they're all mixed. The difference is depends on your problem. For example, in physics-related problems where x would be time, you might want to extrapolate in time. And so you might want to test your model on from T0 to T1. You train your model there, and then you try to extrapolate from T1 to T2 in the future. And this will tell you if you're generalizing in time, if you're able to extrapolate. Because if you're just interpolating, then that's not good enough for a scientific problem. The whole point of, anyway, in machine learning is to extrapolate. So extrapolation, what kind of extrapolation you want to do? If you're sampling randomly, you might not extrapolate as well, or your generalization metric will not be as informative as if you're shuffling. If you're not shuffling, it won't be the same as if you're shuffling. OK, so now we looked at the data. So I will go with not shuffling for now, just to show you how it's clear to see how extrapolation works in that case. So false, and we'll visualize it. We understand. So we see that the trend looks sort of nice. It's not a line. It's something more complex than a line. Looks a lot like a quadratic model, but it could be cubic. Who knows? In most cases, the mapping will be very complex, that you might be able to visualize some of it, but a lot of it will be hard to visualize. But visualization definitely helps you build your feature vector. So let's get our feature vector now, and we'll define a function called makeFeatures. And it'll take an input x and the degree of the polynomial. So I'm going to assume that my feature vector is a polynomial. So here, build feature vector. Or feature, in fact, it's a matrix because it includes all the data points. And I'm going to assume it's a polynomial with a degree, and by default, degree 1, which is just a line with a bias. And now we're going to define this matrix, which has all zeros, and it has a length of x. This is the number of rows is equal to the number of data points. And the number of columns is equal to the number of features. Here we're going to have degree plus 1 features. So if degree is equal to 1, I want it to be a line with a bias. So that's going to be the slope. I'm going to fit the slope and the bias. So that's W0 plus W1x. If it's quadratic, it's going to be a bias plus x squared. Now we just loop through the columns of x and add first the bias, then the first order polynomial, the first degree polynomial, the first degree term x, and then x squared, and then x cubed, etc. So to do that, we'll have to write a for loop in the range of the number of columns. So x.shape will return a vector which will give you first number of rows, then the second element of the vector will be a number of columns. So that's why I'm using shape.1. And I'm going to define all the rows, assign to all the rows xi equals x to the power I. Okay, so this is, and you'll see that this accounts for the bias, because for I equals 0, then whatever x is, x to the 0 will be 1, so that will return 1s for the first column, and this is going to be our bias. And then the rest will be x to the 1, then x to the 2, etc. And then return x. OK, so now we defined our feature vector. There's something about some machine learning problems. They don't like to take y to be shaped just like a vector. Here it's just a 100-dimensional vector, number of data points. Sometimes the output can be more, like 2-dimensional and 3-dimensional. Here it's just 1-dimensional output for y. So 1-dimensional output means that it's basically 100 by 1. So if it's 2-dimensional output, will be 100 by 2. So to just be consistent with some machine learning, I don't know about Sklearn. Sometimes it gave me problems with that. So let's go with reshaping y, and basically recalling it also capital Y, so that we're consistent with the notation. So this is going to be capital Y, and we reshape it to be now 100 by 1. Just to show you, it looks like this now. It's 100 by 1. OK, so we didn't build our feature matrix yet, so let's do that. We just define the function, make features, and take x, which we have already, and the degree d. OK? So let's do d equals 1 by default. So here let's, whoop. No, that's not what I'm doing. So let's call this inputs. OK. Something's happening with my typing. All right. So, and that's, in reality, we shouldn't have split our data at the beginning. If you're doing the learning, you want to start with building your feature matrix first, and then you split your data, so that now you feed in your training set to your algorithm, and then you test it on your test set, etc. So let's do that. Let's do the splitting. So I'm going to copy this and come and paste it here. OK, so paste. OK, so we're going to make everything capital, just to be consistent. Capital Y, and this takes time, more than it should. So capital X, capital Y, X. OK. Now we take this matrix. So we did the splitting here again. Again, we did the splitting again because we're using the feature matrix. And we now, well, let's call it split. And now we perform the fitting. Fit the model. So to do that, we'll define this object linear regression. And all we need to do, well, you should look at the documentation. But in Colab, that's the nice thing about Colab. They will show you the documentation in the notebooks. And so you'll see it's ordinary least squares, and they show you all the possible inputs. You can normalize the data, copy the data, fit intercept. This is an important input that we're assuming. They assume it's true, so by default it's true. But we actually included it in our feature matrix, so we'll set it to equal to false. So fit intercept equals false. And then all we need to do now is just to fit, not get. OK. So let's see if how many errors we have. Whoop. OK. Yeah, of course. That's funny. So to fit data, you need to feed in data to your algorithm. So let's take an X train and X test, well, Y train, sorry. Okay, so now we can actually fit our model, and you see that it's super fast. You already got an answer. And that's why you should use a linear model if you can, because it's faster. It gives you it guarantees an optimal solution. A nonlinear model will probably be much slower, even if it's the same kind of data. But simpler. It's a simple model, so it's faster. Okay. We fit. Let's go back to this picture. So we chose phi. We built phi. We didn't choose any hyperparameters because we assumed their hyperparameters are good enough. But you can see in the documentation of Sklearn that you can change these hyperparameters. We don't have a regularization yet, but you'll see we'll be able to do that with Lasso. And then number of epochs, there's an assumption of number of epochs, but you can increase it, decrease it, etc. So we didn't do that step, but it's assumed. And then we did Sklearn performed this stochastic gradient descent for us. We didn't. It's in the package itself. We didn't have to worry about it. And then now we got to this point where we need to do the evaluation. So evaluate this model. Let's go to another cell and do the evaluation. Well, evaluate model. Now, this linear regression module or function that Sklearn has a built-in evaluation metric, which is the score. And the score is this R² metric. It's 1 if your model fits really well or perfectly, and it could be as negative as possible. So it could be 0, which is sort of you're just predicting the average. And then the more negative it is, the worse your predictor is. So let's see what do we use to do the evaluation? The validation set. So let's do that. Validation, Y validation. What's the score? Negative. Not good. OK, so not good. Why? And this is where we're at this stage, where we got a bad loss. We want to know what's happening. So visualize your predictor, see what's happening, what are the bad predictions. You can look at your worst examples and understand what's happening. For example, especially that's the case with classification. You can look at individual misclassifications and see why you have a misclassification. In this case, it's with linear regression, you don't have that luxury. I mean, it's a different type of problem where you can see which data has the largest error and therefore the worst place for your data. In this case, you'll see that extrapolation is bad. So the more you go forward in X, farther in X, the worse your prediction is. So to do that, let's visualize our problem. Why is it doing badly? I'm going to use X again. And we're going to make the prediction based on this reg function. So to do that, we use the predict function. The predict function will take an array X as before. But it can't take this vector X. We have to build the feature from it. So to do that, we have to make features and take X and degree equals D, as we specified before. And it will predict this. So this is going to be my Y predict, the prediction Y. Now the prediction Y is going to be different from the X. So let's create a figure, plt.figure, and then plt.plot X, Y predict. And let's make it dashed. Of course, I want to plot it also with, here I'm not going to cheat. I'll try not to cheat. we'll take the training set and the validation set, but we won't take the test set, because that's what you should do. Don't cheat and take the test set, because then you can't really test your generalization error. So this is going to be, as we said, OK, so the problem here is our x is going to span all the data. So we want to span only from the beginning of the test set to the end of the validation set. So let's do that. In this case, I know I'm not shuffling the data. If we were shuffling the data, that would have worked. So let's define our x in here to be linspace. It doesn't matter how many points, but it's going to be from 0 to the max of the validation set. And that's going to be x validation minus 1. That's going to take the last element. And let's just do 100. And here, I'm going to use x in. You'll see what I mean when I plot it. OK, and then x in. And so it takes in x in and its prediction, y prediction. We're going to plot the data for x train, x val, and we're not going to use the test data. And then here is going to be prediction. OK, validation. Well, no, now this is train, and this is validation. OK? So let's plot it. That's how it looks. Let's make this red. So the prediction is the line. Everything we predict, any x you give me here, I'm going to predict to be on the line. And you see that how the line diverges in the blue region, which is your validation. And you see why your score can be really bad. And in fact, I'll show you that would be informative. And you want to also do that usually. To test your score also on your training set and see the difference between your training and your test set. If you do, you're usually going to do better. Well, here we're not printing. So we're going to define the val score and the train score. And we're going to print them. Let's print them after the plot. And so print validation score is equal to val score. And training score is equal to train score. So if we do that, now you can see that your training score is very close, or at least closer to 1. It's 0.88. So you're not doing that badly, even though the trend is not a line, but the line sort of does a good job to fit this as well as it can to fit this line. But it doesn't do well at all with extrapolation, because it didn't really capture the trend. And this is the whole point of machine learning, is to capture the trend so that you can extrapolate. And this extrapolation could be in time or in any other metric, depending on what x and y are. And you can see now the validation score is much worse. It's minus 2.8. Now, OK, next. Of course, you can also calculate the root mean square error. In this case, you might be interested to see what's the difference between the points. And the loss, after all, is defined by the square error. You can actually calculate the mean square error. I'm not going to do that now, but maybe later. So let's see. If it's square, it doesn't work. So we go back and change our feature vector. So here, not satisfied, go back and change phi. So we go back and change phi all the way back to here, where we go and say 2. And then that's going to be a square. And now we do better. So we're doing better extrapolating. Of course, we're still doing better on the training set than the validation set, but at least we're not negative in the validation set. And that's the thing, that because we're fitting points with some noise, even though the true model is a square model, you're not going to recover exactly 1. It's not going to tell you exactly, this is it. This is the original model. You unearth the original model. And this is the thing with machine learning. You'll see that maybe with the cubic, well, actually, let's see. With the cubic model, I have to show you the coefficients. That's something I forgot to do. But let's see the cubic model. Well, we did worse. So it actually knows that square model is the best. But before we get into that, let's look at the coefficients. Coefficients of our polynomial, of course. So that's the whole point. We're learning the coefficients of the polynomial. And this is given by reg.coef underscore. Here it is. So this is cubic, so you'll have bias x squared and x cubed. Let's go back to the line, and that's going to be 1. So, well, it gave us this weird model, minus 7 plus 6.5x. Of course, this is, well, it did the best it can, right? If we go to square, so that it gives us something a bit more reasonable. If we run it here, you'll see that, well, the bias is kind of small. There is minus 0.46x, and there's an x squared, 1.1 x squared, which kind of makes more sense. Kind of. We're still not there. And this is what motivates the idea that we want to sort of realize on its own that we don't want a very good bias, a very big bias. Like the bias is kind of small. We want to set it to 0 if possible. And this is the L0 loss I mentioned last time. We want our algorithm to try and include different features on its own algorithmically as part of my gradient descent and get rid of small terms if possible. So that means make it more sparse. Make these elements, if they're small or if they can be made small, to make them 0. And this is where we go into something called Lasso. So Lasso, I'll show you the documentation. This is linear regression example. Also very useful to go through different examples. I wanted to actually show you this, where this is a very simple problem where they import from Sklearn metrics the mean square error, and then they use it to evaluate the mean squared error. We can also do that in our problem, but we'll just go with score now because it's just a good metric in general for evaluation. OK, so this is my cheat sheet. So let's come back here, and I'll have to look up Lasso. Linear models. OK, here it is. So Lasso will do this mean squared error that we've been doing with linear regression. It has this square loss that I talked about last time, but it adds this L1 regularization error. It's just the L1 norm of W, and there's this alpha, which I called lambda. It's how much of this L1 regularization you want to add so that your model is sparse, which means it has as little non-zero elements as possible. And you can see here that alpha is by default 1, and this is one of the hyperparameters. What is alpha? We can loop over it and decide. So to do that, we'll go back to our notebook and replace our model here with Lasso. So we'll keep it square. We'll comment this, and we'll put in Lasso. Now alpha is equal to some a, which I'm going to specify as part of my inputs. A is going to be, let's say, 0.3. Again, it's pretty random, so you have to test it and see how well you do. And based on that, you proceed. And everything else is the same. Because it's the same framework, it's part of the same library. Sklearn makes it as easy as possible to change models. And this is part of your, this loop of trying different models, trying different fees, different hyperparameters. So we're going through that loop now. And now we use Lasso. And, well, you can see that Lasso did a pretty good job getting rid of the first two terms, the constant term, the bias, and the x term. And now we just have the x squared term, and the coefficient is equal to 1.0. That's pretty good, and it generalizes better. But not only does it generalize better, but it gives you a simpler model. And this goes back to this Occam's razor, which is that the simpler the model, the better. If it's not clear why you need a more complex model, it's better to go with a simpler model. And in fact, simpler models in machine learning, as we said, they generalize better. If they do well on your training set, they will generalize better because they don't have high variance. As long as you don't have a high bias. When we started with a line, it was clear you have a high bias, you didn't do well on the training or the validation set. But once we started fitting well, we did pretty well on the training set, you want to consider not making your model more complex. That's not the philosophy with neural networks, where the more complex, the better, and then you use some regularization to make it smooth. But this is the philosophy in science, where we want to come up with simple differential equations or simple linear models that can apply to as many problems as possible. And the sparsifier, this Lasso regularization, is very useful to do that. And it's been used recently to learn differential equations, something I mentioned before. And Nathan and Steve, that have a lot of videos in this series, talk about it a lot. It's called the sparse SIND, which is sparse identification of nonlinear dynamics. I just know it by SIND. But it's basically sparse identification because it actually uses this Lasso, L1 regularization. And by doing that, instead of having linear features or nonlinear feature x and x squared, it has derivative features, dx dt and d2x dx dt squared. And therefore, using that, you can learn differential equation. And you can include derivatives that you don't know if they're possible in the linear, if they're useful in your linear model or not, in your differential equation, and it will get rid of them if they're not useful. OK, enough talking about that. So in practice, now we got to the conclusion of this video. In practice, what you want to do is put all of this process of trying different degrees, trying different regularizers in a loop. You put them all in a loop, and you let your model run for a while. Let's say I'll take this and put it here. I think that's how it works. Let's keep the function out. And this is going to be part of our hyperparameters. So I will define this degree list. Let's say I want to try different degrees, like 1, 2, 3, and 5, OK, and 10. All right, and now I'm going to loop over them for d in degree list. Now d is going to be the first time 1, 2, 3, 4, and then 10. And then we'll see how it does on these different ones. So this is sort of automating this loop. I'm automating this idea. And then for each model, I will get the validation. And then I'll choose the best one. And I'll say, I'm satisfied with this one, and go with test set. The more you automate in machine learning, the better. So we'll do that. And you'll see we get these different predictions. Even with Lasso, although it tries to sparsify the model as much as possible, but it's not ideal. Even in for example, in the cubic case, it'll try to include this extra cubic element to fit the data better. And of course, it all depends on how noisy your data is. If you go to the fifth order case here, now you're starting to overfit, even though the model looks really, really good, where you have 5 terms. You have the constant term x squared, and then x cubed, x4, x5, and it discovers a model that looks a lot like just 1 x squared, y equals x squared, which is pretty good. But now you see, the more you go into more and more complex problems, more complex models, you'll do much better on the training set. You're overfitting, and you'll do much worse on the validation set. That's what overfitting is. But still, reasonably well. Here you see the square term is just 7.9 instead of it being 1, and then it adds all these extra terms to fit the model better, but it's overfitting. Oh, something I did not mention before we conclude is that, this last step, I didn't talk about this, going to the test set. So technically now I'm satisfied with the second order model, let's say. Of course, I'm not doing it here, but what you do is you store your models, every model you learn, so that you don't train it again. And you say, well, the second order is my favorite, so you go with d equals 2, and that will be your model, the one that fits d equals 2. And then you just test it on your test set. So let me just briefly show you what I mean. This is going to be the 10th order because it's just stored the last one. And I'm going to test it on the test set. This is after I finished test and y test. OK? And you see, well, let's assume that for some reason, you chose this model because this is what it last stored in this regression object. So it did really well on the training set. It did worse on the test set, on the validation set. And then once you took that model and you tried it on the test set, it also did even worse. And well, it makes sense. You will do best on training, a bit worse on validation, and worst on test set. Of course, let's just do a small, quick hack here and just add 2, because this will give me the last model to be 2. So this is my last model, second order. And you see here that we have 0.95 on the training, validation 0.65, and the test set actually did better than the validation. This sometimes happens for some reason, but there's no reason why it would happen. And in fact, this is due to the noise. If you don't have enough data, there's a chance that you do better on the test set than the validation set. And this is 0.9. The score is 0.9 on the test set. So pretty good. Your model is pretty good. So you take that and deploy it. And of course, it'll do worse on things that you don't expect, data in the real world, because there are things that you haven't collected. So you get the data in the real world, rework retrain your machine learning problem, go back to choosing your features, do that loop again, and then come back to a test set, and that's it. This is your life in machine learning. So I hope that was helpful. Please ask me questions, send me comments, tell me if there is anything wrong, any bugs in this video, or any thoughts would be great. So thank you for watching, and see you next time.